Okay, welcome to note set 18, where we'll start getting into the details of the DFT. This particular note set, I drew from largely from note sets that I used for my Signals and Systems class, so they should look familiar. And again, this is, I always feel compelled to review. Largely because I feel that I'm building a bridge from things that you learned but may have forgotten or didn't dig all that deep in the previous course. We're trying to solidify that and move forward. So this note set will review some, and then the subsequent note sets will dig into a lot more of the details. So this will set the stage. Okay, so we've been talking about the DTFT, and we've seen that it's a good tool for analyzing discrete time signals and systems as well. I say as we'll see later, but we've actually seen that. So as we've seen, rather than as we'll see later. And so this is the equation for the DTFT. And it's a nice equation for computing analytically if we're given a specific functional form for x of n. We can hopefully, sometimes, if the equation is not terribly difficult, actually find a closed form for x of omega. But in the real world, when we're processing stuff that we're sampling, in comes these samples. We don't know what equation there is to describe that, and we certainly don't have time to figure it out and actually compute this thing by hand analytically. So none of that is actually possible. But yet we want to do this kind of processing to do things like, convert things into MP3 files, do radar processing, all sorts of interesting stuff needs to be done numerically. And so the question arises, well, we've got a bunch of numbers, x of n. Can't we just plug them into this equation and let a computer actually sum those terms up? And well, yes and no. And that's where the DFT idea comes in. So before we get into the specifics of the DFT, let's look at what's causing us to look at yet another new tool with the word Fourier in it. So the question is, why can't we use a computer to just compute the DFT from data? And there's at least two reasons why we can't. And the first comes from the fact, let me erase some of this stuff here so that we can just clear it up just a little bit. First comes from the fact that our equation here goes from minus infinity to plus infinity. So technically, even if we don't collect all the signal samples, those signal samples exist in at least principle if the if we have an infinite number of terms, or at least some very large number of terms, more than we can bring into our computer. So we can't really compute the sum as it's stated for the DTFT because there's an infinite number of terms. Now we could truncate that. Okay, so that's one way to get around that. The second problem, though, is technically the DTFT is defined for every value of omega. All right, we can limit ourselves to minus pi to pi, and then we know that everything outside of that is just a periodic replica. But how many points are there from minus pi to pi? Well, there's infinitely many, and in fact, it's what mathematicians call uncountably infinite. So there are more points between minus pi and pi than there are positive integers. 0, 1, 2, 3, 4, 5, and so on. And so there is no way that we can compute this inside a computer at every value of omega. As engineers, we immediately jump to the following idea. Well, we can truncate this infinite number of terms, so we can handle the first problem. Instead of worrying about infinitely many points, let's just compute it on a finite set of points, a fine enough grid. So we pick a bunch of points, omega, that lie in the minus pi to pi range, and we pick a fine enough grid, and we get a calculation. So we would now have a finite number of terms, and we would be evaluating this at finitely many different omega values. And we can do that. And in fact, that is exactly what the DFT allows us to do. But we need a little bit of formalism that comes because that formalism then tells us how everything behaves. And with formalism comes, what might appear some arbitrary definitions, but we'll eventually get to the point where we are basically just simply saying, yeah, let's evaluate this thing on a grid of points between minus pi and pi while using only a finite number of the terms. And so that's basically where we're heading. And the DFT is just a formalized tool with a lot of specific properties built in by that formalism to allow us to do some mighty interesting things. So let's take a look at this. So suppose we have a finite duration signal. So we know that x of n is equal to 0 outside of some range. So we know that for n equals to 0 out to n equal to n minus 1, so for n terms, we know that the signal is non-zero only in that range. So instead of having to do an infinite sum, most of those terms are going to be 0 because x of n is 0 out there. So we can leave those terms out and we now get a finite sum. So even in that case, if we could compute, if we could imagine summing that up, and we can imagine figuring its values out for every value of omega between minus pi and pi, we might get something that looks like this. And I'll be honest here, I just use PowerPoint's drawing features to just draw some nice curve. I honestly don't know what finite duration signal gives that. And in fact, I don't even know that a finite duration signal exists that does give that. So I just made it up just to illustrate a point. So as we're pointing out down here, we really only need to look at this from minus pi to pi. Outside of that, we know exactly how this thing will get replicated. Now, suppose we decide that we're going to just evaluate this thing at 8 points, and I'm just using a small number 8 so that we can easily see it. In practice, we would want a much finer grid on the omega axis, but just for purpose of seeing it here, I've picked 8 points uniformly spaced. Now, here's the interesting thing. Notice that I don't pick a point at pi because we know that pi and minus pi are exactly the same value. That's because of the periodicity. So same thing, and at 0 and 2 pi it's the same, and so on and so on. So so if I'm looking to determine some points between minus pi and pi, I would leave off the pi. This is just by convention. So you might say, well, what's the harm in putting it in there? Well, technically, from a practical display point of view, there is no harm. But this is part of that formalism that I talked about. By putting it in, we make the mathematical machinery needed to describe how all this works, we make it a little harder to deal with. And if we leave that point out, we get some nice machinery that works really smoothly. And so that's what we do. So and the way that I'm presenting this is not the way that it was developed. It was actually developed more from coming from the smoothly operating machinery to this viewpoint that I'm presenting here. But I have the benefit of decades of understanding Not my own, although, yeah, I've been doing this for decades, but I'm just talking about, the collective knowledge of how this all works and how one should present it. So this is what we're aiming to do, but in reality we would be using thousands and thousands of points perhaps, but we would still not put one at pi because we have the equivalent of that at minus pi. So we don't want any extra redundancy is one way to think about that. Okay, so we've got that set up. And now, even though we're technically interested in the minus pi to pi range, what we're really going to do, and again, this is just, again, because of that formalism, what we're going to do here is instead of computing the negative frequency points, we're going to instead compute these points up here from pi to not quite 2 pi. So now we're leaving off 2 pi because it's the same as omega equal to 0. And again, the reason that we're doing this is because it makes the DFT theory that we're going to end up at, this formalism, makes the mathematical machinery just work more smoothly. And so now, if we think about this, what we're really doing now with this new view is slicing from 0 to 2 pi. We're picking points that are uniformly spaced. The spacing is going to be 2 pi over m, and then we just have to pick an integer k that goes from 0 up to m minus 1. Now, if we did want to include these points instead, we could have just used this same formula, but with k's starting at a negative value and then going through 0 up to a positive value. But that's part of the formalism that that sneaks in here to help us define things in a smoother mathematical way. So instead of taking from minus pi to pi, we go from 0 to 2 pi, and that gives us the spacing 2 pi over m with indices k being integers going from 0 up to m minus 1. So in other words, these are the points that we are looking for. Omega equal to 0, 2 pi over m. So for our case, m is equal to 8 for this picture. So it'd be 2 pi over 8. So that would be pi over 4. And so you can see that we have 1 at 0, 1 at pi over 4. Then 2 times 2 pi over m. That's going to be, for our case, pi over 2, and so on and so on. All the way out to m minus 1 over m times 2 pi. So notice that this number here for the last point is not quite 1. So our last point is not quite at 2 pi. So that leaves the 2 pi spot vacant. Now, if you look at this, what you'll see here is that this is very much like the fence post problem. We don't need a post at the last spot here, but to find out the spacing, we would still take the full 2 pi divided by the total number of points, m. So the reason I call this the fence post problem is, if you said, well, I want to cover 100 feet of fence, and I want to put fence posts every 10 feet, how many fence posts do I need? And invariably, the quick thinking person will just jump to the conclusion that you need 10, because you would take 100 divided by 10 feet and get 10 fence posts. And when you get done with the fence post placement, you'll discover that you have bought one too few fence posts. So this is actually the reverse of the fence post problem. We don't need that final fence post. So we just need a point. So we take 2 pi is the total extent divided by how many bins that we're going to have, and be done with it. Okay, moving on to the next slide here. Mathematically, what we've just done is for a finite duration signal, we are focusing on the finite duration signal case so that we can write this in this fashion with a finite sum without losing any information, because we have assumed a finite duration signal. So the other terms are actually zero. But excuse me, what we've done, we're evaluating at specific frequencies, discrete frequencies, omega sub k, which we are defining to be k times 2 pi over m. And so we see that this is coming from two things: assuming a finite duration signal and picking a uniform grid on the omega axis. And up to this point, we have been letting ourselves be free to pick the value of m so that we can get any kind of spacing that we want. And what we do next, and this is the last little bit of formality here to lead to the official definition of the DFT, we must set m equal to n. So however many samples we put into this computation, we have to have the value of m. So in other words, the spacing set with that same n. So if we do that, we get the thing down here that is in this yellow box, and that is the official definition of the DFT. And you can see that the 2 pi k over n term there, which it's just been rewritten in a slightly different form. So this is the official definition. We've got our k going from 0 out to n minus 1. So technically, these points are giving us samples of the DTFT from 0 out to just shy of 2 pi with this spacing, 2 pi over n. Now, you would think that by limiting m equal to n, we lose the ability to get a fine enough spacing in the frequency axis. But there's a trick called zero padding, which basically allows us to get around this. And I'll say the trick here because it's a little easier to see it here than on a subsequent slide where I actually define it. But the idea is as follows. Suppose I wanted to trick this DFT into giving me a finer grid of omega values. Well, so here's the trick. I'm going to zero pad. So I'm going to create a new signal. Let's call it x hat of n, which will be equal to x of n over n equals 0 out to n minus 1. Okay? So I have that. Let's just think about that in a vector. So x of 0 out to x of n minus 1. And then I'm going to tack on a bunch of extra zeros, however many I want. I'll show 4 here. I'm going to take this whole signal and present it, quote unquote, present it to my DFT computation. So what would happen? Well, the DFT computation would look at that and would say, well, let's see, I need to tidy something up here that I've mistakenly done here. Oh, I can't erase that. After a certain time, I can't erase things, apparently. All right, let me start this over. Here's what I'm going to do. I'm going to create a new signal, which will consist of x of 0 out to x of n minus 1. And then I'm going to tack a bunch of zeros on the end. I'll show 4. So there's my new signal. So the length of this is actually n plus 4 in our simple example here. I'm going to take that whole signal and present it to my DFT algorithm. the DFT algorithm will look at that and say, ah, this is an n plus 4 length signal. So I should put n plus 4 in here, thereby making the spacing, let me erase this here, get back to this. Hold on, hopefully I can erase it now. And of course I can't. All right, let's try to get rid of that. Well, that's not going to let me do it. This program has its advantages and its disadvantages. So I'm going to replace this by n plus 4. That makes my spacing now finer. And imagine if I added a lot more than 4. Say I added 10 or 20. Say I went, say n was 100 and I added 100 zeros. Now instead of having 100 down here, I have 200. So I've made my spacing half what it was before. But let's see what happens to the actual summation. Notice that my sum still really only needs to go out to n minus 1 because those are the only non-zero points. Tacking on those extra zeros don't do anything as far as adding additional terms. No new terms are added. All it does is it changes the spacing on our sum. And so I literally, if I zero pad out so that my total length here is m, I end up back at this equation. So this allows me, by tacking on however many zeros I want, I can make my spacing as fine as I want while still satisfying this idea, this formal machinery that I'm putting in some number of samples, and I'm doing an m, I'm putting in m samples, I'm doing an m term summation, but really only n of those terms are actually being summed because the remainder are 0, but it forces the machinery to make the spacing, the frequency spacing, what I want. I know, it's weird, and for some reason it's the simplest idea. It's a trick, and students get so hung up on this. I don't quite know how else to teach it. It's such a subtle, simple thing. I'm just tricking the math to make it go from this setting back up to this setting while still maintaining this idea that a DFT is by definition n points in, n points out. So I pad it out to m points. I now have m points in. I'm going to get m points out. And that just makes us follow the formalism of this tool called the DFT. And that's all this is about. Okay, that doesn't really cause you much mental anguish. So we're now going to plot our DFT results. And so we have our points with the proper spacing. And remember, we just have the ones that are red here. I'm showing this blue one here. We don't really have it, and we don't need it because it's the same as at k equals 0. So this was the n equal to 8 case. We calculate it, and because we are limiting ourselves here to finite duration signals to begin with, these points lie on the curve of x of omega. So that's a key idea here, but that's only true if the original signal is actually finite duration. Otherwise, we have truncated our summation and we are getting the wrong answer. So we often plot this. Some people plot it on the k-axis. I hardly ever do that. We can tie this k back to the appropriate omega axis by using our formula for where the omega points are, which would just be 2 pi over n is our spacing, and so we just take that number times the appropriate k to find out what the actual omega value is for that point. In the MATLAB demo video, I talked about a simple MATLAB command to always get this right, but that was for after the next step, which will be FFT shift, where we take these top points here and we're going to move them back down here. And so that's the thing that we'll do. Well, not quite the next thing. I'm getting ahead of myself here. Now, one of the reasons we set up all this formalism is so that we have this nice machinery. If we define the DFT this way, with an appropriate value of n, and notice that this x of n may or may not include zero padding. We don't really know. We could be defining, the last 100 samples of that x of n could be zeros that came from zero padding. Now, when we had the DTFT, we could invert it to get back the original signal. And one of the reasons we set up all this machinery the way that we did is that if we compute an x of k this way, then this is the inverse formula for that. And we'll see in the subsequent note set, kind of where this comes from. It basically comes from setting all this up as a matrix operation. And you'll notice that we are going from n signal points to n DFT points and then back. So think about an n by n matrix operating on a n element vector, and then the inverse gives a way to convert back to the original vector. So that's kind of inherent in all the formalism that we're setting up here. But even if you don't know anything about matrices, the idea that we're going from n points of information to another n points of information, and then we're able to come back to the original n points of information kind of makes sense. If we were trying to go from n points to, say, 100 points, or, to some other number, we may not be able to get back the original number if those are different from each other. So that's the key. The formal definition is n points for x of n points for capital X of k, and so those have to have the same number, and then this machinery works just fine. So what do we know so far? You give me n signal data points, may include zero padding, I don't know. And we can compute the DFT. And so far we've only seen, kind of a by hand formula. And we'll want to do this on our computers. And as we'll discuss later, it turns out that, computing the DFT blindly following this equation is very inefficient. And there is an efficient algorithm, computationally efficient algorithm for computing this called the FFT algorithm. So I will just let you in on a pet peeve of mine, and it's important in my mind to keep these things straight. Otherwise, you start missing, you start misinterpreting what things are. So the DFT is a thing. I can point to the result from a DFT computation and say, there is the DFT. That is these things x of k, capital X. The FFT is not a thing that's computed. It is a tool used to compute the DFT. So you'll hear a lot of practitioners and professors and lots of people doing this, and occasionally I will misspeak and I'll say, here is the FFT of my signal. Technically, that's not the FFT, it's the DFT. So, it's kind of like making the distinction between a destination and the route. So this is the destination, this is the route by which we get there. You wouldn't confuse those two things. And if you did, it would tell people that maybe you don't really know what the destination is, or what the idea of a destination is. So anyway, later we will talk about this FFT algorithm in quite a bit of detail and learn how it works. But for now, just recognize that when you compute this in MATLAB, you will be using the FFT command. So we know that you give n signal data points may include some zero padding, which we'll be introducing in just a little bit, although we've already talked about it. So you give me n signal data points, I can compute the DFT. Now, once I have those n DFT points, I can use the inverse DFT computation to get back the n signal data points. And there is a computationally efficient IFFT algorithm to help us go back in an efficient way. And we know that, that the technical formal definition of the FFT gives us points in the upper range of frequencies from pi to just shy of 2 pi. But those things really represent the negative frequencies, and we know that we can move those upper points literally down to represent the negative frequencies, and that's the so-called FFT shift. So this is the command FFT shift that we talked about in the MATLAB set of notes. And just remember that the reason that we define the DFT putting the points in this upper points rather than where we really want them is that it just makes the DFT equations easier to write and easier to work with. So given all of this, we need to understand how we use this to see what an actual signal looks like in the frequency domain. So the DFT together with the FFT are our computational tools, but we do want to tie them back to the DTFT, which we've already seen in our motivational development here. And we want to tie all three of these things together so that we understand when we compute a DFT, we can be sure that we can link it back to some reasonable amount of certainty to what the DTFT looks like and what the CTFT looks like. So anybody can just, armed with a computer, compute a DFT. It's the good DSP engineer who can then say, I can interpret that in terms of the CTFT and the DTFT. So here's what we're doing. We've got some continuous time signal. It just came through some electronics, maybe some sort of sensor like a microphone or a pressure sensor or a temperature sensor, something sensing something in the real world that we care about. And it's probably also gone through some analog electronics, maybe some amplifiers, some filters of some sort, anti-aliasing filter that we've talked about. This may have even come from an antenna after going through, some downsampling, or downshifting, not downsampling, downshifting down to maybe not quite all the way to an equivalent low-pass signal, but something like that, but still real valued in this example, but could be complex valued, in which case we'd have a real part and an imaginary part. Nonetheless, we've got this continuous time signal. It goes through an A to D converter, and we get samples. And our job for right now is to try to see what does the spectrum of this X of t look like. Well, we can't do that directly on X of t, at least not easily and precisely. And so that's why we go into the discrete time world. We now have samples, and the sampling theorem should tell us that those samples are a pretty good representation of the original X of t. And so we stream these into some memory. We are now inside our computer. The A to D converter may actually be inside the computer as well. It's a little ambiguous as to what are the boundaries of the computer. Anyway, we've got a memory array, and we're just stashing samples in there, one right after another. So when we first start this thing up and we say, go, start collecting, that's time equal to 0, n equal to 0. So we've got the 0, the 1, the 2, all the way down to n minus 1. We shove those samples into our memory array, and then once we're done collecting them, we say, okay, clock strikes or some sort of event happens, and we say it is now time to compute the DFT of this. And so if we do that, we now have some hardware or software or some combination of hardware and software that will actually take these numbers and effectively compute the DFT of them to get these capital X of 0, capital X of 1, all the way down to capital X of n minus 1. So notice same number here as here. That's our rule. When we compute a DFT, however many numbers go in, that's however many numbers come out. So we're not talking about zero padding yet. We'll get to that in just a little bit. And I comment here that we're actually more than likely going to be doing this using the FFT algorithm. And I say the FFT algorithm. In reality, there's many different forms of FFT, but people still tend to say the FFT. Okay, great. So this processor crunches on this set of numbers here and creates another set of numbers, and it writes them into a memory array. Now, it may write them into exactly the same memory array or a new memory array. That depends on whether you need to keep these time domain signals around for something else. But that's totally application dependent. So this is the scenario. And so here's what we want to do. Let me clear some of this out here. Given this computed set of numbers that we now have, we would love to be able to look at those on a plot and use those to interpret what is the Fourier transform of x of t. What does it look like? Where are there strong frequency components? Where are there weak frequency components? Are all the strong frequency components down around DC and then fall off as we go to higher frequencies? Or is there not much around DC, then some strong ones in the middle, and then it falls off again? Those are the kinds of things that we want to do. And we've seen already in the MATLAB examples the capability of doing that. We looked at a guitar signal, and we did some FFT processing on it, and we discovered that we could plot it, and from the discussion we had there, I was pointing at that thing as if it was the actual Fourier transform of that guitar signal. It's going to be pretty close, and that's one thing we want to do here, is to understand what affects pretty close and how close can we get to be pretty close. And so we need to understand what impact our decisions along the way here have. And so in this picture, there's only a couple decisions that we can see that we've made. How fast did we sample our signal, and how many samples did we collect prior to doing our DFT processing? Now, there will be a few other things that will come into the mix here as we go through, but for right now, this is the simplest scenario. But I'll give you a hint. We hardly ever process exactly like I'm showing here. We do some additional stuff. Zero padding, which we've already alluded to, and some sort of windowing. We apply a taper to this data, and we'll talk about why we do that in our later note sets. Okay, let's go on to the next slide here. So we want to connect the DTFT and the DFT. And we did that as we were motivating the idea of DFT for one specific case. We said, suppose our signal is finite duration. Then we could immediately write out the exact form for the DTFT for that finite duration signal, and we could actually then evaluate that at a discrete set of omega values. And so that's what we're talking about here, but we also want to ask what happens, and this is more of the practical case, what happens when the signal really is infinite in duration? Now wait a minute, you're saying no real-world signal can really be infinite. Well, okay, at least it has a duration longer than what I can get inside my computer. Now, it may be that I can't get it all inside my computer because I don't have enough memory, but it could also be that I just don't have enough time to wait. So if I'm trying to do some sort of radar signal processing, I can't wait forever to collect all of the signal samples from my radar or from somebody else's radar that I may be trying to do some electronic warfare against. I can't wait that long. I have to collect a small amount of data from some much longer, though not really infinite, but still so long that I might as well just say, you know what, I can think of this signal that I can't really collect as being infinitely long. So what is the impact on all of this ability to try to see what the Fourier transform looks like? What's the impact of being able to see only a snippet of the actual signal data that I could have if I had more memory and or more time to collect? And that's the goal that we need to strive towards understanding, because this is what happens in the real world. I've got some chunk of data, but how do I relate it and make sense of it, relate it back to the true CTFT? So we will look at these two cases separately. The finite duration case, the less practical scenario, is the easier one to understand. Isn't it always that way? So we'll handle this case first. Armed with that understanding, we'll then move on to the infinite duration case. All right, next slide. So let's look at this. We're dealing with the finite duration case, and we've already kind of gone down this road, so I'm just going to reiterate it here. So if x is finite duration, so it's 0 outside of the n equal to 0 to n minus 1 range, we can truncate this sum. We don't have to really technically truncate it because the terms outside of this range are 0, so we just leave those out. So that's what the finite duration case allows us to do. It tells us that the actual DTFT can be written precisely, exactly, in terms of a finite sum. And that finite sum is something that I can do more easily because I don't have to sum up infinitely many terms. But as we already said, it still has this pesky continuum variable there. And we already said, oh, here's what we do with that. We evaluate this at a certain set of points, 2 pi k over n, where k runs from these over these values, 0 out to n minus 1. And we look at this and we say, aha, yes, that is exactly the DFT equation. And we can compute that using the FFT in an efficient way. And we know what we get from that. We get samples at these particular points, samples in the frequency domain that are spaced by 2 pi over n. But more importantly, because this is just computing this at discrete omega, and that actually links back to this, we are literally computing the true DTFT at these discrete points. So that's what I'm showing here when I say, well, I can't get rid of that now. Let's try to get rid of it this way. There we go. So that's what I'm saying here when I say that the DFT points are exactly equal to samples spaced every 2 pi over n of the actual DTFT. So cross, that's the DTFT, that's the DFT. So this big yellow box here is what we've just established, and you know me by now. If you're taking this course, you probably already took my Signals and Systems course. You know that when I put a result in a big yellow box with a red line around it, red border around it, it's an important idea. And it generally encapsulates the big idea that we just developed. So for the finite duration signal case, the DFT points lie exactly on the DTFT. Now that only holds true for the finite duration signal case because we were able to transition from an infinite sum to a finite sum and then just evaluate at specific values of omega. Okay, so just reiterating this, that we have a signal x of n. We can think about its DTFT. We can think about its DFT. And the DFT is equal to samples of this only if we're talking about the finite duration case. Now, I tuck in this idea of zero padding. This has nothing to do with the finite duration case, which is why I tried to talk about it earlier, because that's probably a better place to talk about it. But we will use the symbol NZ often, not always, to be the number of samples after we have tacked on some number of zeros. So we have n actual samples, we tack on some number of zeros, and we now have a total number of samples, non-zero and zero, which will be equal to nz. And so our spacing is now 2 pi over nz. So this is just a trick that allows us to, without having to tell anything to the DFT machinery, and really that means the FFT algorithm. You just take your signal samples with a bunch of zeros padded onto the end, you shove it into your FFT algorithm, and it says, oh, I see how many samples you gave me. This is the spacing I should be using, and that's what it does. So this is just a cheap and dirty trick to get the FFT algorithm or the direct DFT algorithm, either one, to do what you want it to do without having to get in and change the internal machinery of that. All right, so big idea. Finite duration signal, points of the DFT lie right on the DTFT of the finite duration signal. Great. Let's look at a simple example. So suppose we have a little rectangular pulse. So x of n is 1 from 0 out to 2q, and it's 0 otherwise. And this is just going through some little bit of subterfuge with a specifically defined function that shows up on the DTFT table on my Signals and Systems web page. We define this p sub q rectangular pulse as being 1 from minus q out to plus q. So what we really have is a q shifted version of that. So we saw that the DTFT of the zero-centered rectangular pulse has this sink-like structure, and then to get the thing that we actually have, we are shifting it by q, so we get this little extra exponential term due to the delay property. So, so if that's our actual signal, or our actual DTFT, we know that since this is a finite duration signal, if we collect at least 2q plus 1 samples, so we go all the way out and at least get all of those ones and maybe some of the zeros beyond, and if we compute the DFT of those things, we will get points that are just evaluations of that at our appropriate grid. So our grid points will be k times 2 pi over n, where n is the total number of points that we are collecting here. And so we will, for the moment, assume that n is equal to 2q plus 1. So we'll get an evaluation that looks like that. So that's just a simple, stupid textbook problem that says, apply this idea that you just learned to something that you can do on paper. But what happens if we were actually to process this kind of? Here's what we would get if we collected the samples and then zero padded. So for Q equal to 5, we're going to end up with 11 actual non-zero values, and then we're going to zero pad 11 zeros onto it so that our n after zero padding would be 22. And we can see, I've done some MATLAB computations here, and I'll go through the code on the next page. But the blue curve is actually the theoretically computed DFT plotted. And the dots, well, actually the stem plot, are computed numerically with the FFT algorithm and then properly plotted to match up. And so you can see that in this plot up here, where we had 22 points after zero padding, we end up with points that are right on the DTFT. Now, notice that the way that I've set this up here is very important. The way that I've set this up here, let's see if I can get rid of those. No, I'll try to get rid of it this way. The way that I've set this up here is I have, in this case, I have 11 non-zero points, and then I have 11 zeros. So if I did no zero padding at all, my spacing would be twice what it is here. And so remember that technically our DFT starts at 0. So I would have this point, and then my spacing would be twice what it is now. So I would not have this point, and I would have this point. And I'd not have that one, and I'd have this one. And I'd not have that one, and I'd have this one. And not that one, but this one. And not that one, but this one. And not that one, but this one. And this one, and this one, and this one, and this one. So if you look carefully at the ones that we have, it's one non-zero value, and everything else looks like 0. Everything else is 0. So if we were to plot this DFT result with no zero padding, it would look like I get a delta function. It would look like I just processed a sinusoid, which I did not. I processed a rectangular pulse. So that's the beauty of zero padding. Without zero padding, we plot this result and we are getting a false picture because we are seeing points spaced so widely that they are not necessarily filling in all of the intermediate points on the DTFT that we should be seeing. Okay, so that's that, but let's take that idea a little bit farther. If we take our 11 non-zero points and pad on 77 zeros, now we're up to, after zero padding, an NZ of 88. So now my spacing is going to be 2 pi divided by 88. And you can now see, if we just look at just the dots, and in this case, in reality, I would get rid of the stem plot and just plot the dots. But I didn't do that. But even just looking at the dots, you can really make out the structure much better than up here, right? Up here, if I were just seeing just the dots, I'd be kind of motivated to think that those are connected by straight lines. I can't see what the curve is. But now when I have a much finer grid, due only to zero padding, notice that from the points, I can really make out the structure of that underlying DTFT. And that is the exact correct underlying DTFT because it was a finite duration signal and I collected at least as much as the full signal. And by the way, I could get this case, since this is a single rectangular pulse, I don't really have to zero pad here. I could just keep collecting all the way out to 88 points. And I would just naturally collect those zeros that I've been padding. So either way gets me there. But I wanted to do it with zero padding to illustrate that what does zero padding do for you? It allows you to fill in the gaps and better see the underlying DTFT. And in this case, since it's a finite duration signal, that underlying DTFT is the exact correct DTFT that I want to be viewing. And we'll revisit that idea when we get to the infinite duration case. So here's the code that I used. Now, you might have been thinking, wait, how did he actually calculate that DTFT if he's saying that he can't really compute a DTFT? Well, I computed it with a little trickery because I had an equation for it, but I still had to compute it on a very, very fine grid, so fine that it just looked like it was on a continuum. And then I just plotted it with a regular plot function. So here's the equation that we had derived for the DTFT, and notice that I left off the e to the j term. That was just a phase, and I was really only going to be plotting magnitude, so I kind of left that off. I set my q value. I create an omega vector here with a very, very fine spacing that really pretty much goes from minus pi to pi, and I add this EPS variable. That's an internal automatically defined variable in MATLAB unless you overwrite it, and usually not a good idea to do that. EPS is the smallest number that MATLAB can represent, and so I add that to my vector here because I'm going to be going through the omega equal to 0 point, and if I try to evaluate this equation for the DTFT at omega equal to 0, I will get the numerator evaluates to 0, the denominator evaluates to 0, and I get 0 over 0. And MATLAB will squawk about that and will give you a warning or an error. I can't remember which one it does. I think it gives you an error of some sort. So I use the EPS so that for this part, when it evaluates to 0, I'm going to add this very small number. It just tweaks it just a tiny little bit off from 0, not so much that you can even see any difference, but enough that MATLAB will evaluate the numerator and denominator and not get 0 over 0, and it will actually get the correct value. So just a little trick that I came up with along the way. So the rest of this stuff here is just plotting that DTFT plot. And then down here, you can see where I start to do the actual DFT processing. So what I do here is I initially just fill X with 22 zeros, and then I fill the first 11 points with 1. So I'm kind of actually doing this backwards from what you would normally get in the real world. In the real world, you would get your 11 samples, and then you'd tack on your 0 pads at the end. I just sometimes when I know that I'm going to 0 pad, I just fill up something with zeros and then stick my actual samples into the front of that vector. Also, if you go back and revisit what we did in the MATLAB demo video, you may remember that the FFT command itself has a built-in way to do 0 padding. So if I do FFT, say X, comma, NZ, and if NZ is an integer, positive integer that is bigger than the length of X, then the FFT command will 0 pad out to a total number of NZ. Now listen carefully, here's the catch. If NZ is less than the length of X, then before the FFT is computed, it will truncate X to that shorter length and then compute the FFT with no 0 padding. So it's kind of a double-edged sword. It's very convenient, but you got to know what you're doing and how to use it, which is the case with any double-edged sword or chainsaw or circular saw or any power tool. You need to know what you're doing. So hopefully you know what you're doing. And then here's this FFT shift command that we talked about back in the MATLAB video. And so the FFT shift just takes those upper frequency parts that go from pi to shy of 2 pi and moves them down to the minus pi to shy of 0 range. So that's all that does. And then here is computing my omega vector for my DFT. And you can see there's the spacing, 2 pi over 24 times the k values. So I'm just following exactly like what we just saw in this set of notes, as well as the kind of command that we talked about in the MATLAB demo. And then the rest is just plotting. And then down here, I'm just redoing everything for zero padding out to a length of 88. So you can see I start with filling X with 88 zeros, and then I stuff my non-zero ones in. And then the rest is the same. So I'd encourage you to kind of study this code, see how it works, and make sure you understand how it works. Okay, so just summarizing the key ideas that we saw for the finite duration case. This is the finite duration case. The DFT points that we compute lie right on the DTFT curve. So you give me a finite duration signal case if I've collected at least as many samples as the finite duration signal has non-zero samples. I collect those. I can see perfectly what the DTFT is. And remember that DTFT can get linked back to the CTFT through sampling theory. And we'll talk about that later. We've also seen that zero padding helps. It doesn't change the actual shape of the DFT. We're still just getting points on the curve set by the underlying DTFT. It just gives us a denser set of points, but they all lie on the true DTFT. So in this case, zero padding gives us a better view of this perfect view DTFT. Okay, and so that summarizes the finite duration case. And now we want to talk about the infinite duration case. So we cannot, in a computer, collect infinitely many samples. First of all, we don't have enough space. Secondly, we don't have enough time to wait. So suppose we've got some signal that we're imagining goes on forever, or at least longer than we're willing to collect samples. And suppose when we start collecting samples, we'll define that to be n equal to 0. And so we collect from n equal to 0 out to n minus 1. And so we've grabbed n samples. And so we can, and we'll call those x of n. Actually, I just misspoke. We will not call those x of n. So x of n is the infinite duration signal. We can link the samples that we've collected of x of n to some new signal, which we'll call x sub capital N, which is equal to the samples that we've collected, where we collected them, and 0 elsewhere. So in other words, this is sort of like chopping off, setting to 0 the parts that we didn't collect. And to link this to ideas that we'll talk about later, it's like applying a window, right? You look out a window, you can only see so far to the left, so far to the right. It's truncating what you know is out there in reality that goes on forever and forever, but you can only see a certain amount. And so if we imagined a window that's set to 0, whatever it is that we're seeing, and whatever that means, I don't know from an image, actual physical seeing point of view. But here we're just saying, here's what I can see, and for the purposes of analysis, we will imagine setting everything else to 0. So listen, I just said for the purpose of analysis. In reality, all we're doing is collecting n numbers, and we put those into memory somewhere. To understand what's going on, the analysis part, we imagine this new signal that has zeros everywhere we didn't collect. Okay, and so now we can imagine if we just do a DFT of our collected samples, we can imagine rewriting that in terms of n samples from this truncated or windowed signal. And so we can put a sub n down here, and that sub n is there to tell us that this is the DFT of n samples collected from some much longer signal with samples that we didn't actually collect. And the question that we want to know is, what does this DFT show us? How can we relate that back to the DTFT of the full duration signal? Now you might say, how on earth could we do that? Obviously we can't know what the infinite duration signal's DTFT looks like, but we can get a feeling for what it will look like, or what kind of impact it could have had. This finite duration collection, what kind of impact, what does it do to us? What kind of thing does it cause? What kind of error? And we'll be able to characterize that. So to talk about all these different things, we need to call different things different names. So we've got our infinite duration signal computed, DTFT computed over a continuum. So we'll call that x sub infinity of omega. Now that is the holy grail right there. That's the thing that we really want to be able to see, but in our computers we have no hope of getting that for two reasons, remember. Infinitely many samples and on a continuum. Okay, so given that, that's our x sub infinity. The next thing we'll define is what we just defined, or at least related to what we just defined. We're going to say, all right, take this thing and just truncate it to n terms. So calculate, instead of n equal to minus infinity to infinity, go n equal to 0 out to n minus 1. So obviously this is some incorrect version of our original DTFT. It's not going to look right because we don't have all the sums that are needed in there. We're missing some. So it's some sort of distorted version of what we want to see. And what we want to know is, how are these two things related to each other? Is there some sort of characteristic way that they get related to each other? And finally, the thing that we can actually calculate, because we still can't even calculate that because it's on a continuum from minus pi to pi. What we can calculate is, we take those n samples, we put them into a DFT, and we can calculate this quantity. So we have xn of k, xn of omega, and x sub infinity of omega. And we want to see how these things are all related to each other. So one thing we do know already, though, we do know how xn of k is related to xn of omega. So let's think about that for a minute. Notice that this is the DTFT of a finite duration signal. The finite duration signal, that is just x of n from n equal to 0 to n minus 1, and then 0 outside of that range. So this is the DTFT of a finite duration signal, and this is the DFT of that same finite duration signal. So this DFT must give us samples on that. So that's a key idea. So the DFT that we can compute no longer gives us samples on the DTFT we really want to see. It gives us samples on some distorted version of what we really want to see. And so understanding that is very important to knowing how to apply these ideas. Okay, so and that's captured right here in this this big yellow box. The DFT of our collected data does not perfectly show the DTFT of the complete signal. It shows the DTFT of the truncated signal, which is some sort of distorted version of what we really want. So our goal is to understand this kind of error. And there's actually a name for this kind of error, and we'll see what that is. So we want to see how these two things are related to each other. So if we think about applying, this is that window idea, we think about applying a rectangular window here that zeroes out the values that we didn't collect. And so we have already found the DTFT of that window function. It's a rectangular window. I'm setting up some terminology and language that we'll use later. So we're applying a rectangular window to the infinite duration signal to create this n-length windowed signal. Technically, this signal goes on forever, but it has non-zero values only from n equal to 0 out to n minus 1. Now, we have a property of DTFTs that says if we have a signal, if we have two signals multiplied, we can find the DTFT of the product. So I've got x of n times p sub q. I know the DTFT of the multiplying window, and so I can now write the DTFT of this thing right here is this frequency domain convolution of the two DTFTs. So here is my infinite duration DTFT. Here's the DTFT of my rectangular window. And this equation is a frequency domain convolution. And since omega is on a continuum, it's done with an integral, not with a summation. And so this is actually called smearing. Another term for it is called leakage. Let me see if I can type this in here rather than trying to I'm trying to write it out. So leakage is another term that's used. I like smearing better because it kind of says a little bit more what it looks like. There's a reason that it's called leakage, and we'll get to that at some point. But basically, what we're seeing is that the thing that we would really like to see, which is this thing, gets smeared into this thing, which is what we can really see from this. Now, as we collect more data, this rectangular window becomes longer and longer and longer, and no surprise, this thing becomes a sharper and sharper spiked thing. Starts off looking like a sinc function, but it becomes more and more and more like a delta function. And so if you remember sifting property, if this thing actually went to a delta function, then this would be exactly equal to x sub infinity. It would just sift it right out. So the more we can make this thing look like a delta function, the less smearing we will have. The broader that this DTFT looks, the more smearing we will have. And the longer we collect, the more this thing will look like a delta function. And so we get this big idea down here. Collecting more data is good. No kidding, right? I'm trying to see something that has infinite amount of data. If I collect a small amount, it's going to probably look horrible. The more I collect, the better it should look like the real thing. So no big surprise there. Okay, so let's take a look at how this actually works and connect these things together. So up at the top here, we've got x sub infinity. And I've, again, just drawn some nice visible, recognizable shape. I'm not saying that this is really any kind of real DTFT that you would ever expect to get. And so you collect some finite amount of that signal samples, and if you could figure out what the DTFT of that truncated signal looks like, which you can't, but if you could, this might be what it looks like. So there's some sort of smearing, and so the smearing that we generally see has a couple characteristics. We're not seeing all of the characteristics in this little cartoon version here, but what we're seeing is that kind of sharp edges kind of get smoothed out. So that's the underlying DTFT of the truncated signal, truncated to n samples. And remember, as we let n get bigger, so as we collect more samples, the middle curve will look even more and more like the upper curve. But for right now, we're saying that's what we got. So we've collected n samples, and what we can actually compute using the DFT, computed by the FFT algorithm, are these dots down here. So those are the dots that would be the values computed by the DFT plotted at the correct frequency points. And I've also used FFT shift so that this part that's down here actually started up here. FFT shift moves it down there. Okay, so we've got let's see here. Clear this off a little bit here. So that's the deal. And if we zero pad, we will only get a finer spacing. So if we zero pad, we can get points in between here. It's a little hard for me to draw those in. We can get a finer spacing, so we would still have the black dots, and we would have all those red dots that I just added in if we zero padded to twice the length of what we collected. We would have the spacing between our DFT points. Notice that zero padding does nothing to change the shape of this. That only comes from the amount of data that we've collected. Now, the only other thing that we're not talking about here is, remember, this is the DTFT, so there may be some aliasing that occurs in this, so that's an error that we haven't talked about here, but could be present. And we'll talk about that in just a subsequent slide. But understanding this connection is key. If you can capture this idea, then you are well on your way to knowing how to use a DFT and interpret it properly. So this tells us that zero padding only helps us see this better. So as good as that is, we can see it. As bad as that is, we can see it. Zero padding doesn't help us do anything to improve that. So here's a summary of the important points for the infinite duration case, and this is really the case that we would really run up against in the real world. So the effect of having a finite amount of data is that we get a smeared version of the infinite duration data DTFT. Then when we compute the DFT points, which are really the only thing that we can really see here, all the others were just drawing, for these cartoon cases. But in the real world, we don't have those. We just have the points. So think about it. You get the points, and you have to try to guess. Does this look right? Does it not look right? So you need to make sure that you've done your analysis properly ahead of time so that for the class of signals that you're interested in, things will work well enough to do what you're trying to do. So the DFT points lie on the smeared DTFT curve, not on the true DTFT curve. And then zero padding gives us a better view of this imperfect smeared DTFT. So if the smeared DTFT is crap, the more we zero pad, the better we'll see that crap. Is one way to think about that. Okay. So here's a nice relationship, a nice plot or figures that show kind of all the relationships here. So We've got x of t coming into the A to D converter, x of n, imagined to be an infinite duration signal. We collect n samples, we do our DFT processing, and we get n DFT points. And this should give you an idea of how all of this fits together and where the errors come from. So we are seeing 3 different errors here. This is the thing that we'd ultimately like to see. There's no error in that. That's the exact thing that we're trying to visualize. Now, we sample that with an A to D converter, and we may end up getting some aliasing here. That's coming from the spectral replica having a tail. Well, I didn't quite nail that. Let me see if I can get this a little bit better here. No, not letting me do it there. Let's try it this way. There we go. Of course, I moved that some. Okay, let me try this a little bit better here. There we go. So that's the part of the spectral replica that's been shifted out to be centered at Fs, that's folding back in and creating aliasing error. So if you add those 2 things together, you end up getting this elevated region here. Okay, so that's the effect of aliasing. And how do you fix that? Well, sample faster. That's the only way to fix it. Because as soon as you have improperly sampled, you've got aliasing in this, and there's no way you're going to get rid of it. Okay, so we are now stuck with this aliased full DTFT, and so that is theoretically what would be here. We cannot see that. We're just drawing it as an iconic representation of what would be there. None of this that we've talked about so far can we actually see. Then we collect a finite amount of data, and as soon as we do that, we've committed to having available to us only a view of this truncated, smeared DTFT. And so that's what we have here, and we can see that these nice sharp spikes have been smoothed into broader, less obvious spikes, and that's one of the effects of this aliasing. And then finally, we do our DFT processing, we compute, and we plot our DFT results, and all we can see are the dots here. We can't see that dashed line. The dashed line is just this smeared DTFT put on top of it, but that's all we can see. And if we look at that and we try to connect the dots, notice that we might not even see these little blips that have been smoothed from what they really are. Let me try to get rid of some of this stuff here. So we can't really see the blips that we can barely see here, that we could better see there, that are in the actual CTFT. So suppose that's the feature of interest. And maybe that tells us something. Maybe if we see that spike and we can figure out at what, A, it's there, B, what frequency is it at, we can determine, maybe like in the movie Hunt for Red October, we can determine, aha, I see signs of the presence of a submarine and its motor is spinning at this, this RPM. We could probably figure out all that stuff from this perhaps, but we collected our data, we process it, we don't even see that spike even though it's really there. So what would we do to try to improve our ability to see that spike? Well, what we would do is if we collect more and more data, the smearing will look, the smeared version will look more and more like this. And then if we make a real fine grid, we'll have lots of points. It's kind of hard to draw on that, but I bet I can do this. Let me see if I can get fancy here. I think I can zoom in and then draw, but let's see. Let's see if I can do that. Oh, yes, and I can rotate. So let's suppose that we collect a lot of data so that x sub n looks almost like this x sub infinity. And since we've collected more data, our spacing is going to be finer, but let's suppose that we even go overboard and tack on lots and lots of zeros. Now here will be the test of whether I've succeeded here. And we can get a very fine spacing. And then we'll be able to see the existence of that spike, and we'll be able to measure precisely where it is. Okay. Ha. I think I'm mastering this tool. So hopefully that puts into perspective how this all works. Let's go to the last. This just kind of summarizes what we've just seen and what these errors are and what we can do to control them. As we go through the A to D converter, the CTFT gets converted to the DTFT sub infinity, and we can have aliasing error there. And the only way that we can control that is through proper choice of our sampling rate. If we've improperly sampled, then we've got no hope of fixing the impact of that aliasing error. Now, there will always be some amount of aliasing error there, as we've talked about, but the point is that we need to sample fast enough so that aliasing error is made negligible enough that it won't affect what we're trying to do. The next progression takes the DTFT sub infinity into the DTFT sub n, and that will result in smearing errors or leakage error. I prefer to call it a smearing error. It's not at all a standard term, but I'd like to make it a standard term. The more common term is leakage error. But nonetheless, you get kind of a smeared version. The only ways that you can control that we've talked about so far is the choice of n. So if you collect more data, you will have less smearing error, and that's good. This slide comes from my Signals and Systems class, where I say, well, if you want to know about this windowing thing, see a DSP course. Well, now you're in that DSP course. And so later, a few note sets ahead, we'll be talking about windows. So remember, we talked about effectively, when we go from the infinite duration signal to a truncated version of the signal, we modeled that by multiplying the infinite duration signal by a rectangular window. We will choose different shaped windows and think about the analysis of that and see what impact that has on the smearing error and figure out some trade-offs that we can make that will improve things even without increasing the number of samples. So now these three things are things that we really don't have access to in the real world. But we're using thoughts of those to understand what we really do get when we compute the DFT. So finally we compute the DFT. The grid error is because we're only seeing certain points on the underlying DTFT sub n. And so I call that a grid error, and the error might be that there could be a spike in between the points that we compute that we just simply cannot see. And the grid error is controlled by any means that will give you a finer spacing. So to some extent, the choice of n will help, but not always. Your real tool to combat the grid error is zero padding. So once we've settled on a DTFT sub n through our choice of n and our choice of window, then zero padding comes into play to try to get a fine enough view of this quantity so that our DFT will show everything that we need. And then I just summarized down here the zero padding trick. So we'll finish there, and hopefully, the zero padding trick didn't seem too, too strange. Like I said, in my experience, that's the one thing that students tend to stumble over for some reason. But hopefully you got it, and I'll see you in the next slide.